This is the Empire State Building. You already know it. 102 floors. One of the most recognized structures on Earth. But here's what almost nobody talks about. In 2009, engineers quietly began one of the most ambitious retrofit projects in the history of modern construction. Not a new building, not a new skyscraper, a full-scale, deep engineering overhaul of a structure that was already 78 years old. The budget? $550 million. And the result changed how engineers think about buildings forever. This is the story of a hidden mega project quietly built within one of the most iconic structures on Earth. The problem nobody wanted to admit by the mid-2000s, the Empire State Building had a serious problem. It was hemorrhaging energy at a rate that would embarrass a modern warehouse, let alone a landmark skyscraper sitting in the middle of Manhattan. The numbers were honestly brutal. The building was burning through about 38 million kilowatt hours of electricity every year. Its heating and cooling systems weren't just outdated, they were struggling to keep up. And the windows, every single one of the 6542, were old, single-pane glass from decades ago. In the winter, they let heat slip right out. In the summer, they pulled in so much solar heat that the entire system had to run nonstop just to compensate. The building's carbon footprint was enormous, and operating costs were climbing every year. For any other building, the answer might have been simply tear it down and start again. But this was the Empire State Building. Demolition wasn't a conversation anyone was having. The challenge handed to engineers was something far harder. Take a 1931 skyscraper and make it perform like a 21st century building, without shutting it down, without displacing 15,000 daily occupants, and without touching the iconic exterior that made it a protected landmark. What followed was one of the most complex engineering challenges in the history of building retrofits. Building an assembly line inside a skyscraper, the first and most visible problem was the windows. All 514 of them. Modern high-performance windows are triple pane, argon-filled, low-emissivity-coated units. They are thick, heavy, and expensive. Simply ripping out the original windows and installing new ones sounds straightforward, until you realize that the original frames were load-bearing elements integrated into the limestone facade of a protected historic landmark. You cannot simply remove them. The engineering team came up with a solution that had never been attempted at this scale before. They decided not to replace the windows at all. Instead, they would rebuild them from the inside. Each original window was disassembled on site. The original glass was removed, cleaned, and reused as one of the outer panes. A new inner glass pane was added. Between them, engineers injected a suspended film, a thin, transparent layer coated with a heat, reflective metallic coating, and then sealed the entire assembly with a new thermally broken frame. The result was a remanufactured window that performed almost identically to a modern double pane-low emissivity unit at a fraction of the replacement cost, and without altering the exterior appearance by a single millimeter. But here's where things get seriously impressive. Think about it, handling 514 windows one by one, floor by floor, in a fully occupied skyscraper. That would have taken years, and the labor costs alone, completely out of control. So the engineering team took a completely different approach, something no one had ever pulled off in a retrofit project before. They literally built a factory inside the building. On one of the lower floors, they set up a complete window remanufacturing assembly line. Windows were removed from their frames, sent down to the factory floor, processed through the assembly line, and reinstalled. All within a single working day per window. At peak operation, the team was processing over 70 windows every single day. This was not renovation. This was manufacturing, inside a skyscraper, while 15,000 people worked above them. The cooling problem and the radical solution windows were only the beginning. The Empire State Building's HVAC system, the heating, ventilation, and air conditioning infrastructure, was a patchwork of equipment from multiple decades, running at catastrophic inefficiency. The cooling load alone was staggering. On a hot summer day, The building's air conditioning demand peaked at roughly 10,000 tons of cooling. That is approximately the cooling capacity needed to air condition a small city neighborhood. The core issue was what engineers call plug load diversity. Essentially, the building's mechanical systems had been designed around a worst-case scenario. Every tenant running maximum equipment on the hottest day of the year simultaneously. In reality, that scenario almost never happens. But the equipment was permanently sized and permanently running as though it would. The engineering solution was a complete chilled water plant overhaul. The original system was replaced with a centralized plant using variable speed chillers, machines that can dial their output up or down in real time based on actual demand rather than theoretical maximums. This alone was a radical shift in how the building consumed energy. But the engineers went further. They introduced a thermal energy storage system. During off-peak nighttime hours, when electricity is cheaper and the grid is under less strain, the system runs the chillers at full capacity, not to cool the building, but to freeze enormous tanks of water into ice. Then, during peak daytime hours when cooling demand is highest, that stored ice is used to supplement the chillers, dramatically reducing the peak electrical load. The building essentially banks cold overnight and spends it during the day. And this one system alone made a huge difference. It cut the building's peak electricity demand by about 1/600 kilowatts. That's like taking the power use of more than 200 average American homes off the grid exactly when demand is at its highest. The tenant problem. Engineering meets human behavior here is something most engineering breakdowns of this project leave out entirely. The engineers ran the energy models. They installed the new windows. They rebuilt the mechanical systems. And when they calculated the projected energy savings, they hit a wall that no amount of engineering could solve alone. Even after all the upgrades were done, a lot of the wasted energy was still coming down to everyday habits. Lights left on in empty offices. Server rooms kept far colder than they needed to be. Space heaters running under desks, fighting against the building's own heating system. Monitors and equipment quietly sitting on standby all night. It wasn't the building anymore. It was how people were using it. The engineering team made an unusual decision. They brought the tenants into the project. Each major tenant received a detailed energy dashboard, a real-time display showing exactly how much energy their floor was consuming, hour by hour, compared to neighboring floors. This was not a guideline or a suggestion. It was data, live, visible, impossible to ignore. The behavioral change was measurable. Tenants began competing. Floors started turning off lights. Server room temperatures were raised to industry standard levels. The aggregate impact of tenant behavioral changes contributed an additional 10 to 15% reduction in energy consumption beyond what the physical upgrades alone achieved. This was a lesson that has since been written into engineering guidelines for retrofit projects worldwide. The best mechanical system in the world is only as efficient as the people operating inside it. The numbers? And why they changed everything when the full retrofit was complete and the results were measured over a full operational year. The figures that came back stunned even the engineers who had designed the project. The building's annual energy consumption had dropped by 38%. Not from demolition, not from a ground-up rebuild, from a retrofit of an existing 1931 structure. Annual energy cost savings came in at $4.4 million per year, every year. Locked in permanently by the physics of better glass, better chillers, and better building management systems. The retrofit also achieved LEE Gold certification, one of the highest sustainability ratings in the construction industry. To put that in perspective, a building constructed in 1931 using steel and concrete poured nearly a century ago is now outperforming the energy efficiency benchmarks that most modern office towers struggle to meet. Carbon emissions from the building dropped by more than 105,000 metric tons over the decade following the retrofit completion. That is the equivalent of taking roughly 22,000 cars permanently off the road. achieved entirely by re-engineering a building that already existed. The project's ROI calculation was straightforward and devastating to any argument against the investment. At $4.4 million in annual savings against a $550 million investment, the pure energy savings payback period runs long, but the engineers and building owners were never calculating only energy savings. The retrofit transformed the building's market position. Premium tenants demanding modern, sustainable office space. Tenants who would previously have looked at a century-old building and walked away began signing leases. The retrofit did not just save energy. It saved the building's competitive position in the Manhattan office market for the next generation. The legacy, a blueprint for the planet. Here is why this project matters far beyond one building on one block in Manhattan. There are approximately 5.9 million commercial buildings in the United States alone. The vast majority of them were built before modern energy codes existed. They are inefficient by design, not because of negligence, but because the engineering knowledge and materials to build them better simply did not exist when they were constructed. Collectively, commercial buildings account for roughly 18% of all energy consumption in the United States. Replacing all of them is economically and physically impossible. The materials, the cost, the time, and the carbon cost of demolition and new construction would exceed any benefit for decades. The only viable path is retrofitting them, making what already exists perform better. Doing exactly what the Empire State Building did. The Empire State Building retrofit was not just a construction project. It became a documented, published, open-source case study, a model that engineers, city planners, and building owners in over 60 countries have now studied and adapted for their own retrofit programs. Cities from London to Seoul to Sao Paulo have used the methodology developed on the 34th Street block of Manhattan to overhaul their own aging commercial building stock. The window remanufacturing technique developed for this project has been adopted on dozens of subsequent historic landmark retrofits globally where replacement was architecturally prohibited. The Tenant energy dashboard model pioneered here is now a standard feature in smart building management systems sold worldwide. A single retrofit project on a single 1931 building produced an engineering playbook that is actively reducing energy consumption in buildings on every inhabited continent. The Empire State Building is famous for what it looked like when it was finished in 1931. But the engineering achievement that may actually matter more happened 78 years later. When a team of engineers looked at a century-old skyscraper and refused to accept that old buildings had to be inefficient buildings, they built a window factory on the 4th floor. They froze water at 3 a.m. to cool offices at 3 p.m. They handed tenants live data and watched behavior change in real time. And they proved that the most sustainable building is almost always the one that already exists, if you're willing to engineer it properly. $550 million, 38% less energy. A blueprint used on 6 continents. Not bad for a building that was already old when your grandparents were born.